In this video, we will discuss the calculations for the precision and accuracy of laboratory glassware experiment. Please keep in mind that you are only required to show the calculations for one trial for each of the three glassware types. Please do not include calculations for all of the trials. We will walk through the calculations for the three glassware types that we investigated. First the beaker, then the graduated cylinder, and finally the burette. Each of the calculations will be similar for all three glassware, but there will be a few differences. Recall that the beaker can only be read to the ones place for the volume. This means that the volume read from the beaker for all three of your trials will be 10 milliliters. Following this, there are 5 remaining calculations. First, we have to calculate the mass of the water delivered. Second, we calculate the volume of the water delivered. Third, we calculate the average volume read from the beaker. Fourth, we calculate the average of the calculated volumes. And lastly, we calculate the standard deviation of the calculated volumes. First, we will calculate the mass of the water delivered by the beaker. To do this, we need to subtract the mass of the empty beaker from the mass of the beaker and the water. We will be using data that I collected. For this example, trial 1 found the mass of the empty beaker to be 28.357 grams, and the mass of the beaker with the water to be 34.939 grams. Therefore, the mass of the water is equal to the mass of the beaker and the water minus the mass of the empty beaker, or in this case, 34.934 grams minus 28.357 grams, which gives a value of 6.582 grams of water delivered. The remaining 2 trials of my data, the masses were found to be 6.940 grams and 7.023 grams. Your numbers will be slightly different. Next, we will calculate the volume of water delivered using the masses calculated in the previous calculation. To do this, we need the density of water and equation 2 from the experiment PDF. Recall that the density of the water is determined from the table using the temperature of the water as recorded in the lab. I measured the temperature of the water to be 22.8 degrees Celsius. The corresponding density of water using 23 degrees Celsius is 0.997538 grams per milliliter. Therefore, the volume of water is calculated as the mass of water divided by the density, or for trial 1, 6.582 grams divided by 0.997538 grams per milliliter, giving a volume of 6.598 milliliters for trial 1. For my data for trial 2 and 3, the volumes were found to be 6.957 milliliters and 7.04 milliliters. Now we need to calculate the average of the volume read from the beaker and the average of the actual delivered volumes. To calculate the average volume read from the beaker, it is simply the average of 10 milliliters read 3 different times, or 10 plus 10 plus 10 milliliters divided by 3, which is equal to 10 milliliters. We can now determine the average of the calculated volumes of water that were delivered. Recall that the volumes for this example were found to be 6.598 milliliters, 6.957 milliliters, and 7.040 milliliters. Thus, the average volume delivered is equal to 6.598 milliliters plus 6.957 milliliters plus 7.040 milliliters divided by 3, which gives 20.595 milliliters divided by 3, or an average of 6.865 milliliters. Lastly, we can determine the standard deviation for the calculated volumes delivered by the beaker. The first step to this is to calculate the deviation for each volume. Recall that the deviation is merely the measured value minus the average. For the first reading, the deviation is 6.598 milliliters minus the average of 6.865 milliliters, or negative 0.267 milliliters. The second deviation is calculated as 6.957 milliliters minus 6.865 milliliters, or 0.092 milliliters. The third deviation is found to be 7.040 milliliters minus 6.865 milliliters, or 0.175 milliliters. Next, we need to square each of the deviations. The square of the first deviation is negative 0.267 milliliters squared, which is equal to 0.0713 square milliliters. For the second deviation, we get 0.092 milliliters squared, or 0.0084 square milliliters. And lastly, for the third deviation, we get 0.175 milliliters squared, or 0.0307 square milliliters. The final step is to complete the standard deviation. Recall that we begin by summing the square deviations, dividing by n-1, and then taking the square root of that result. In this case, we have 0.0713 square milliliters plus 0.0084 square milliliters plus 0.0307 square milliliters, all divided by 3 minus 1. This gives 0.1104 square milliliters divided by 2, or 0.0552 square milliliters. When we take the square root of this value, we have determined our standard deviation to be 0.235 milliliters. Now we can work on the graduated cylinder. Recall that the graduated cylinder in this case should be read to 1 decimal place. This means that the volume read from the graduated cylinder will be 10.0 milliliters for each trial. The calculations for the graduated cylinder will be almost identical to those for the beaker. First, we calculate the mass of the water delivered. Second, we calculate the volume of the water delivered. Third, we calculate the average volume read from the graduated cylinder. Fourth, we calculate the average of the calculated volumes delivered. And lastly, we calculate the standard deviation of the volumes delivered. As with the beaker, to calculate the mass of the water actually delivered, we need to subtract the mass of the empty beaker from the mass of the beaker and the water. For my data, trial 1 was found to have the mass of the empty beaker to be 28.398 grams, and the mass of the beaker with the water to be 38.408 grams. Therefore, the mass of the water, which again is equal to the mass of the beaker and water, minus the mass of the empty beaker, is 38.408 grams minus 28.398 grams, or 10.010 grams. For my data, trial 2 and 3 had masses of 9.938 grams of water and 9.925 grams of water. We can now calculate the volume of water actually delivered, again using equation 2 from the PDF and the previous density as determined. Since the temperature of the water has not changed, we use the same density, 0.997538 grams per milliliter. Thus, the volume of the water is equal to the mass of the water divided by the density, or 10.010 grams divided by 0.997538 grams per milliliter, which gives for trial 1 a volume of 10.035 milliliters. For trial 2 and 3, the volumes were found to be 9.963 milliliters and 9.949 milliliters. We can now calculate the two average volumes. First, the average volume is read from the graduated cylinder, which is just the average of 10.0 milliliters read 3 different times, or 10.0 milliliters plus 10.0 milliliters plus 10.0 milliliters divided by 3, or 10.0 milliliters. Now we can determine the average of the 3 calculated volumes delivered by the graduated cylinder. Recall that the volumes for this example were found to be 10.035 milliliters, 9.963 milliliters, and 9.949 milliliters. Therefore, the average volume delivered is 10.035 milliliters plus 9.963 milliliters plus 9.949 milliliters divided by 3, which gives 29.947 milliliters divided by 3, or an average volume of 9.982 milliliters. We can now determine the standard deviation for the volumes delivered by the graduated cylinder. As before, the first step is to calculate the deviation for each of the measurements. The first deviation is calculated as 10.035 milliliters minus the average value of 9.982 milliliters, which gives a deviation of 0.052 milliliters. For the second reading, we have 9.963 milliliters minus 9.982 milliliters, or negative 0.020 milliliters. Finally, the third deviation is 9.949 milliliters minus 9.982 milliliters, or negative 0.033 milliliters. Next, we need to square each of the deviations. For the first deviation, this becomes 0.052 milliliters squared, or 0.0028 square milliliters. For the second deviation, we have negative 0.020 milliliters squared, or 0.00039 square milliliters. And lastly, for the third deviation, we have negative 0.033 milliliters squared, which is equal to 0.0011 square milliliters. And finally, we can complete the standard deviation. In the numerator, we have 0.0028 square milliliters plus 0.00039 square milliliters plus 0.0011 square milliliters. In the denominator, we have again 3 minus 1. This gives 0.00429 square milliliters divided by 2, or 0.215 square milliliters. When we take the square root of this, we determine our standard deviation to be 0.046 milliliters. Now we can consider the burette. Recall that the burette should be read to 2 decimal places, and that each burette reading must be calculated separately from the initial and final volume readings. For my data, Trial 1 had an initial volume reading of 13.21 milliliters and a final volume reading of 23.20 milliliters. To calculate the volume that was read from the burette, we take the difference, or the volume read is equal to the final reading minus the initial reading, which is 23.20 minus 13.21 milliliters, for a final volume of 9.9 milliliters. Trials 2 and 3 had stated volumes to be calculated as 10.0 milliliters and 10.01 milliliters. The remaining calculations are largely the same as before, with one small difference. Again, we calculate the mass of the water delivered first. Next, we calculate the volume of the water delivered. Then we calculate the average volume as read from the burette. Next, we calculate the average of the calculated volumes. And finally, the standard deviation of the calculated volumes. As with the previous examples, to calculate the mass of the water delivered, we need to subtract the mass of the empty beaker from the mass of the beaker and the water. For my data, Trial 1 was found to have a mass of the empty beaker to be 28.392 grams, and the mass of the beaker with the water delivered to be 38.347 grams. Therefore, the mass of the water is equal to 38.347 grams minus 28.392 grams, or 9.955 grams. For trials 2 and 3, the masses were found to be 9.965 grams and 9.985 grams. We calculate the volume of the water delivered in exactly the same way as before. Again, we use the same density, 0.997538 grams per milliliter. As before, the volume of water is equal to the mass of the water divided by the density, or 9.955 grams divided by 0.997538 grams per milliliter, which gives the volume of water for trial 1 to be 9.980 milliliters. For trial 2 and 3, the volumes were determined to be 9.990 milliliters and 10.010 milliliters. Now we can calculate the two averages of the volumes. The average volume read from the burette, as before, is simply the average of the three readings, but this time the three readings are all different. This gives the average volume read to be 9.99 milliliters plus 10.00 milliliters plus 10.01 milliliters, all divided by 3, or 10.00 milliliters for my data. Now we can calculate the average of the volumes delivered as determined from the masses. Recall that the volumes for this example were found to be 9.980 milliliters, 9.965 milliliters, and 9.985 milliliters. Therefore, the average volume delivered is equal to 9.980 milliliters plus 9.965 milliliters plus 9.985 milliliters divided by 3, which is equal to 29.980 milliliters divided by 3, or an average volume of 9.993 milliliters. Lastly, we can now determine the standard deviation of the volumes delivered. As before, we begin by calculating the deviation for each of the volumes. For the first measurement, we get 9.980 milliliters minus the average of 9.993 milliliters, or negative 0.013 milliliters. For the second deviation, we have 9.965 milliliters minus 9.993 milliliters, or negative 0.0033 milliliters. And for the third reading, we have 9.985 milliliters minus 9.993 milliliters, or 0.017 milliliters. Next, we square each of these. For the first deviation, we have negative 0.013 milliliters squared, or 0.00018 square milliliters. For the second, we have negative 0.0033 milliliters squared, or 0.000011 square milliliters. And lastly, for the third, we have 0.017 milliliters squared, or 0.00028 square milliliters. Now we can complete the standard deviation. Our numerator has 0.00018 square milliliters plus 0.00011 square milliliters plus 0.00028 square milliliters. And again, our denominator is 3 minus 1. This gives 0.00047 square milliliters divided by 2, or 0.00023 square milliliters. When we take the square root, our standard deviation is found to be 0.015 milliliters. Now that we have completed all of the calculations, we can compare the glassware. We will start by comparing the accuracy. To do this, we need to compare the average volume delivered as calculated to the stated volume as read from the glassware. These values are given in the table below. First, for the beaker, the stated volume was 10 milliliters. We found the average volume delivered to be 6.865 milliliters. Next, for the graduated cylinder, the stated volume delivered was 10.0 milliliters. Our average calculated volume delivered was 9.982 milliliters. Lastly, the burette had an average stated volume of 10.00 milliliters, and the calculated volume delivered was found to be 9.993 milliliters. As can be seen, the value of the average for the burette is closer to the stated volume than the other two pieces of glassware. Therefore, we determined the burette to be the most accurate piece of glassware of the three. Lastly, we can compare the precision. To do this, we look for the glassware that has the smallest standard deviation as calculated. These values are stated in the table below. For the beaker, the standard deviation of the volumes delivered was determined to be 0.235 milliliters. The graduated cylinder was found to have a standard deviation of 0.046 milliliters, and the burette had a standard deviation of 0.015 milliliters. Clearly, the burette has the smallest standard deviation and therefore is the most precise piece of the glassware. We can now discuss the report. In addition to this video, you will find several files posted on Canvas. These are the files that you will need to write your report. First, there will be a report guidelines. This is a list of instructions to walk you through all of the calculations and the questions that you need to answer. Secondly, you will find a data sheet. This data sheet is a fillable PDF. You will need to download the PDF and save it to your computer. You can then open the PDF using Adobe Acrobat, Microsoft Edge, or some other PDF program. You need to type your data and the answers to the questions into the PDF and then save it again on your computer. The report will consist of the data sheet that you just saved, along with the answered questions, and your sample calculations. You must show every calculation listed in the report guidelines to receive full credit, but you only have to show them for one trial for each piece of glassware. These calculations can be uploaded as photos. However, I recommend that you install the Office Lens app on your phone. It is available for both iPhones and Androids. You can use this app to save a photo as a PDF for upload to Canvas. You will upload the data sheet and the calculations to Canvas. If you have any questions regarding this video, please contact me as soon as possible.